Uh, this is a talk. Uh, it's an expanded version of a talk I gave back in October, and I've added quite a few more topics. And it's just sort of a random selection of topics loosely connected with a common theme of antennas and electromagnetics. Uh, and I'm here basically to answer your questions. If you have questions on this stuff, I'm going to explain a few ideas that engineers use that hams may or may not know about. Most engineers will know all of these concepts. And then I'll get into a few little fine details, and then I'm going to talk about the overall picture here. So let's go on to the next slide. You've seen this. This is just the summary. Go ahead, next slide. Here are my topics. We'll start off with cats, and we'll move from cats to the nature of physical laws, and then a little bit about, so just some comments on physics in general, and then we'll talk about some antenna properties. And in particular, we'll talk about feed point impedance and antenna Q and radiation, which are interesting aspects of antennas, usually are connected to radiation. And then some references at the end. I'll show you which antenna software modeling programs are currently the best. You know, it keeps changing, but the current best antenna modeling programs for those of you who like to do numerical antenna analysis on computers. Okay, next slide. Okay, Albert Einstein was asked, how does radio work? And Einstein answered, you see, wire telegraph is a kind of very, very, very long cat. You pull his tail in New York, and his head is meowing in Los Angeles. Do you understand this? Okay. And radio operates exactly the same way. You send signals here, they receive them there. The only difference is there is no cat. Next slide. However, cats are connected to radio in interesting ways that we shall see. There's a great British poet, T.S. Eliot, who wrote a book called Old Possum's Book of Practical Cats, which is a collection of poems about cats. In there, and also Andrew Lloyd Webber did a musical called Cats, based on T.S. Eliot's poems. And in both stories, there's one particular cat named Old Deuteronomy, who's like the senior cat, the top cat. And his job is to sort of like set down the laws for all the other cats in a particular tribe called the Jellicle cats. And every year he sends one cat, bestows an honor, gives them a job, a title and a job. And that cat goes up, 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 past the Russell Hotel, up, 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 up to the Heaviside Layer. There we see some interesting ideas. People who do literary analysis have never figured this out. They don't have a clue. You can read all the bizarre misinterpretations on Google if you wish. But what T.S. Eliot was telling us is that cats handle HF radio propagation in the ionosphere. And we'll see in a moment what explains band openings. But there is one error, the word Russell Hotel. Eliot used the word Russell Hotel. Well, there is a Hotel Russell in London, but that's not the hotel. The hotel the cats go past on their way to the ionosphere is not the Russell Hotel, it's the Hilbert Hotel. Every mathematician knows what the Hilbert Hotel is. Is there anybody here who is a mathematician who knows what the Hilbert Hotel is? Okay, the Hilbert Hotel is a hotel that has an infinite number of rooms. And it's due to mathematician David Hilbert, who was a German mathematician. And the reason Eliot got this wrong was because he wrote this in 1930 when the hot topic wasn't German mathematics. It was British work in logic. And the Russell refers to Bertrand Russell of Russell and Whitehead, who wrote Principia Mathematica. And what was hot in those days was the fact that Bertrand Russell and Whitehead had written a monumental work called Principia Mathematica, which attempted to derive mathematics from more fundamental principles of logic. In other words, the foundation of mathematics rests on an even deeper foundation of symbolic logic, and That was in the news. That was a hot topic. That was in all the newspapers. And that was what Elliott knew. And this was written only 5 years before Kurt Gödel's famous incompleteness theorem, which he knew nothing of. So he got the hotel wrong, but he got the idea right. What is this hotel of infinite number of rooms? We won't go into that tonight, but we will say that the cats go beyond it, even higher, something bigger than and beyond infinity, all the way up to the heaviside layer. Now, who knows what the heaviside layer is? What it refers to. Heaviside layer, you know it as the ionosphere. Oliver Heaviside. And the word ionosphere didn't come into the language until the early 1940s, it was early 1940s. It was experimentally discovered and confirmed by Edward Victor Appleton in the early 1930s, around 1934. They actually confirmed that the ionosphere was real and existed. But before that, it had been hypothesized by Oliver Heaviside as an explanation. And who was Heaviside? He's the famous Scottish mathematician who worked out Maxwell's equations. In fact, the equations we call Maxwell's equations in the form that they're in are actually Heaviside's equations. Yes, simplified them by making the notation more complicated. But the equations got shorter, but each symbol means a lot more. Okay, next slide. Band openings. Back one, there. Schrodinger cat. Everybody knows about Schrodinger's cat, right? This is the cat you put in the box. You have a little switch connected to a tube of, I don't know, cyanide gas. And you have a little trigger mechanism, and it's based on whether a certain particle decays or not. The cat either, the cyanide is either released or not released, and you don't know which. And until you actually open the box to observe the cat, the cat is actually in a state of superposition, mathematical superposition, meaning he is both alive and dead. And only when you open the box and observe does it collapse the wave function. This is a term from physics due to Niels Bohr. It collapses the wave function, and the cat is either alive or dead. But up until that point, when you observe him, he's both alive and dead. And so Schrodinger's cat was very famous in physics. Nobody ever opened the box. His wave function never collapsed. He's still 50% alive and 50% dead. And since cats make the ionosphere work, we see that explains band openings. With probability 50%, the band is either open or not. Next slide. So what about physical laws? We've all heard about things like Ohm's law. Is there anybody here who has heard of Ohm's law? Everybody has heard of Ohm's law. Good. And Ohm's law states that if you have a resistor and there's a voltage V across the resistor, then there's a current I through the resistor, and it gives you the relation between the current and the voltage. The relation is E equals IR. Sometimes we use what are called magic circles to explain the Ohm's law in licensing classes. Now, that means that if you put a 1 volt voltage source across a 1 ohm resistor, you will cause a 1 amp current to flow. But it also means if you put a 1 amp current source across that same resistor, the resistor will develop 1 volt across its terminals. So the voltage in Ohm's law doesn't cause the current, and the current doesn't cause the voltage. They simply coexist, and they mutually satisfy a relationship called Ohm's law. Maxwell's equations are exactly the same way. Exactly the same. The equations are descriptive. An if-then, and the if-then is a logical relation that's the equation describes. It's not describing a cause and effect relation. It's describing an if-then logical relation. This is true of all of Maxwell's equations, and it's true of almost all the laws of physics, is that they're not explaining cause and effect. They're explaining if-then relationships among quantities or variables. So in particular, electric and magnetic fields coexist, but an electromagnetic wave has an electric part and it has a magnetic part, but neither part is the cause of the other part. And this corrects a common confusion. So let's go to the next slide. You've all seen this picture. It's in lots of ham radio licensing material and the handbook and everything else. And they'll say that the time varying electric field causes a time varying magnetic field, and this explains wave propagation. Nonsense. The two waves coexist. They're part of the same thing. They're part of the electromagnetic wave. They travel together. Neither causes the other. The time varying magnetic field does not cause a time varying electric field and vice versa. So that's the error. Instead, both fields originate from a common source. It's usually a time varying current source, and they're generated together. They travel together. They go at the same speed, and neither causes the other, but they're both caused by the current source that originated back at the source. And there's equations called radiation integrals that tell you how these waves behave. We won't go into radiation integrals. Let's go to the next slide. So here's some fictions. There's plenty of fictions. This is just the tip of the iceberg. A dipole should be 1/2 wavelength long. Anybody ever heard someone say that? Half wavelength dipoles are resonant. Has anybody ever heard someone say that? I think I've heard this more than once. Dipoles are 75 ohms or 73 or 72 or some number in that neighborhood. In free space, a half wavelength dipole has a real resistive feed point impedance. A half wave dipole is 50 ohms. Wow, we went from 75 to 50. Is that even true? No. The feed point resistance of a half wavelength dipole depends on its diameter. That is not true. That is not true. The feed point reactance of a half wavelength dipole depends on its diameter. That is actually, well, we'll come to that. Those two are tricky, and I'll explain why in a moment. Dipoles are anti-resonant lengths slightly longer than an even number of half wavelengths. Okay, we don't need that one tonight. Let's go on. Here's some statements that are opposite to those. These are statements that actually are true. Simple dipole is defined as an entity that is symmetric and center fed, and it's also a wire of some diameter, usually constant diameter. Usually constant. If it's not constant diameter, then we don't call it a wire, we call it a body of revolution, and it can be a cone or a conical, or it could be two dissimilar cones. But if it's just a straight circular cylinder shape wire, then we call it a simple dipole. It is center fed though. That's kind of like by definition. So the term off center fed dipole is kind of an oxymoron. It's no dipole is off center fed. If you off center feed the dipole, it shouldn't be called a dipole because dipoles have symmetry. Off center fed dipoles do not have symmetry about their center point. We'll ignore the source symbol there. That's my own invention based on the earlier slides. The AC does not stand for a cat. AC stands for alternating current. For lossless antennas, directivity and gain are the same. That's true. That means the directivity pattern and the gain pattern are the same, but that's only for lossless antennas. An antenna's radiation resistance is not unique. It depends on a reference current or location. That is true. So when we talk about the radiation resistance of an antenna, we have to state that we're going to refer it to a particular point along the antenna or a particular point along the current distribution. Once we specify that, then the antenna will have a unique radiation resistance relative to that definition, relative to that point. So antenna radiation resistance is usually defined at the current node along the structure, or it's defined at the center point. The resonant length of a dipole depends on its diameter. That's true. The resonant length depends on its diameter through a formula or a number we call the K factor, and I'll talk about the K factor in a moment. Dipoles are resonant at lengths slightly shorter than an odd number of half wavelengths. That is a true statement. I will make a distinction at some point between a resonance and an anti-resonance, but we don't need to see that now. Here's the formula. Resonant length of a dipole at a resonance is K times lambda over 2. It could be K times N times lambda over 2, where N is a multiple. And then we have to put a subscript on the K because the different Ks for different resonances. Dipoles are anti-resonant at lengths slightly shorter than an even number of half wavelengths. That's true. If a linear antenna is resonant and its feed point impedance is real everywhere along its length, which means you can slide the feed point to the left or the right. It won't be a dipole. It'll be an off-center fed dipole, but no matter where you move it, right, the impedance will be real. If it's resonant in this at the point in the center, it's resonant everywhere. Linear antenna is a straight line antenna. Straight line, like a wire, straight wire, not an L, not a curve, not a surface. And let's see, the last one. If a dipole is a half wavelength long, then its current phase is about 30 degrees everywhere along its length, taking the 30 degrees relative to the phase reference. The phase reference will take to be the phase of the voltage at the feed point. Yes, yes. So the fact that they're not in phase tells you that the half wavelength dipole is not resonant, slightly inductive. Okay, next slide. Impedance varies as a function of frequency. The ARRL likes to show this plot on the left, which is a semi-log plot. We have resistance on a logarithmic axis. The horizontal axis is resistance, and it's a logarithmically scaled axis. The vertical axis is reactance, and it's a linearly scaled axis. So this is what we call a semi-log plot. And as frequency changes, we can see how the antenna's impedance spirals around in this almost triangular spirals on the impedance plane chart. Now, engineers never use that figure because engineers like to use the diagram on the right, which is called a Smith chart. And there we see, and I won't explain Smith charts, but there we see that the impedance spirals around in nice concentric circular spirals. And Smith charts are very handy for doing all kinds of calculations and for learning how to do impedance matching through very intuitive techniques. So without math. So the Smith charts are very handy, and that's why they're very popular. And these particular impedance curves are for a thin wire antenna, number 10 wire, 98.4 feet long, length to diameter ratio of 11,000, frequency sweep from 1 megahertz to 30 megahertz. Just for reference, this is an HF thin wire antenna, about 100 feet long. Okay, next slide. Now we can represent the impedance of a dipole by an equivalent circuit. An equivalent circuit is a circuit made up of inductors, capacitors, and resistors. And for the sake of discussion, we'll call them ideal resistors, ideal inductors, and ideal capacitors. So these are mathematical abstractions. Real physical inductors and capacitors obey the properties closely, but not exactly. If you sweep over a wide enough frequency range, they don't behave the same. Okay, so here's five. There's five. The series RLC circuit in the center is the equivalent circuit that is commonly used. It's the most common equivalent circuit, but it's also the least accurate over frequency. It's good at one frequency. If you vary the frequency a little bit, it degrades very rapidly. So it doesn't track the impedance across frequency, and it won't behave on the Smith chart the way I showed you those spirals did. More accurate are the two that are at the top, left and right, the 3-element circuit and the Tang-Tian gun 4-element circuit. Those are more accurate, and more accurate still is Sergei Shelkinov. He was a Russian mathematician at Bell Labs. His circuit, the bottom left, and my own 5-element lumped element circuit on the bottom right. Those are the most accurate over bandwidth, but you can get even more elaborate and get even more accurate equivalent circuits if you add elements, if you connect them in the right way. So let's look at what happens. Let's go to the next slide. So here I've got a 1 meter long dipole. I don't know how we get far off the title, but anyway, 1 meter long. Okay. Oh, great. Now we can see the title. It's a dipole. I'm going to sweep it from essentially DC to 1.5 gigahertz, it's a pretty broadband sweep. And we're going to see how the impedance varies between this equivalent circuit that I've constructed versus the equivalent circuit impedance, the reference impedance, which we'll compute by NEC, NEC4 or NEC2, whichever I used. So let's go to the next slide, see the results. There we have it. So we've got an equivalent circuit that tracks all of the spirals of the antenna on the Smith chart pretty well. Let's go to the next chart and we'll look at it in Cartesian coordinates. And there we see the blue curve overlaid with a yellow dashed curve. And that's the real part of the impedance. And we see the red curve overlaid with some other color dashed curve. Yeah, I can't tell what color it is from here, and you probably can't tell either, but there's a dashed curve and a solid curve overlaid on the top and on the bottom. One is resistance, the one on the bottom is the reactance, and they track very well. All I'll say is they track very well. So it shows that you can construct equivalent circuits that match the impedance on the Smith chart extremely accurately if you use the right circuit topology, which means all the right elements connected the right way and the correct values for all those elements. Okay, let's see the next chart. SWR, same thing. Same antenna, and you always have a dashed curve and a solid curve. The solid curve is neck 4 and the dashed curve is the equivalent circuit. And back again, we're going all the way from DC out to 1.5 gigahertz on a 1 meter dipole. Okay, next slide. Okay, let's talk about this mysterious factor K that I was talking about. Next slide. We have two definitions of resonance. And this is a confusing concept because people will throw around the word resonance, resonant and resonance loosely without actually saying which definition they're referring to. So one definition of resonance defines resonance as the frequency at which the energy in the electric field and the energy in the magnetic field are equal. As you go through one RF cycle, the energy moves from the magnetic field energy to electric field energy and then back again. But the amounts of energy stored in both fields is equal. So that's one definition of resonance. And if you increase the resonance, if you increase frequency, more energy will be stored in one field and less in the other field, and you'll be out of balance. The other definition of resonance is a definition of this based on things you can measure at the feed point, the impedance of the antenna. And antenna is resonant if the reactance is 0. So at any frequency for which the reactance of the antenna is 0, that's a resonant frequency. Okay, we have two definitions. The question is, are they equivalent? And the answer is no, they're not equivalent. They lead to different resonant frequencies, different ideas about resonance. And we'll see why in a moment. But basically, you can take any non-resonant antenna and simply modify its structure to make it resonant through impedance matching. This has no effect on the fields that are actually in space. Putting in a matching network at the feed point does not affect the fields that are in space. So the same ratio of electric to magnetic fields will be present whether you put a matching network at the feed point or not. And since I can arbitrarily move the reactance around with a feed point network, there's no reason why you would expect the resonant frequencies under the second definition to be the same as the resonant frequencies under the first definition. Okay, let's go to the next slide. Dipole resonance. Okay, well, we go back to the beginning. Here's two sources that are fairly old, where the phenomena of resonant length is discussed. So let's go to the next slide, and we're going to see some curves. The curves on the left were published by the ARRL from 1947 to 1997. And the curve on the right was published starting in 1998 up to 2018. What happened is very interesting. Somebody thought that they could do a better job by using Next software to compute the curve rather than using the old formulas. So they computed it. They came up with a different curve. They look similar, but when you overlay them, they're not. Now, the other interesting thing is that up until time of this change, the RSGB in Great Britain, they have their own antenna book and their own handbook, and they were publishing their own curve. They finally decided after all these years that they were going to drop their curve, which was based on Shelkonoff's theories, and publish the ARRL curve. So the same year that the ARRL dropped the curve on the left, the RSGB started publishing the curve on the left and all their stuff. And ARRL moved on to this curve on the right, which is even less accurate than the curve on the left. So what is this thing called K? Well, it's the factor you multiply the half wavelength, the free space half wavelength by to get to the resonant length of the dipole. They said dipoles that are resonant at the first resonance, they're slightly shorter than a half wavelength. K is a number that's slightly less than 1. It's about 0.95, 0.92, but it's a number less than 1. And you can see that from the vertical axis on these two graphs. We're dealing with numbers that range from 0.93 to 0.99. Okay, let's go to the next slide. Unraveling this took me almost a year. I went back and I looked at every paper and book published on, and every book and author had their own different idea about this K curve. They're all over the place. They all look the same until you overlay them. When you overlay them, you see, oh, they're all really different. And so this is what I saw, all these different curves. The ARRL's first curve tracks the orange curve on the top, or the green dots on the top. The ARRL's second curve tracks the black squares on the bottom. Everybody else is in the middle. Okay, let's go to the next graph. Figuring out who is right requires figuring out what is K and how do you get it. So one theory is that K is a velocity factor. Well, it's not a velocity factor because the dipole, there's no physical basis for a velocity factor different from unity. Shelkonoff did a wave theory on bicones, and he used unity as his velocity factor and got very accurate results. And there's no one's explained why you would have any other velocity factor for a thin wire dipole. So velocity factor is not the reason. K is an end effect. Some people claim that K is due to something that happens at the end of the antenna. However, if that were true, then the forward and the reverse traveling waves would interfere to give you a sinusoidal current distribution along the antenna. And all that would happen from an end effect is to readjust the phasing of that standing wave. But that's not the current distribution. The current distribution is not sinusoidal, not exactly. And so the theory that K is an end effect falls apart. Third theory is K is due to current distribution not being sinusoidal. Well, that also falls apart. So it falls apart because the induced EMF method gives you very accurate values for K, and it assumes sinusoidal current distribution. So all three of these theories have serious problems, conceptual problems, and can't be the reason behind this K factor. It can still be predicted accurately by the induced EMF method. And it can be computed by method of moments if you use the right computer codes, not NEC. but something more accurate. Okay, let's go to the next slide. I'm looking through this and reworking the whole problem from scratch. I started with Carter's, what are called the Carter equations for antenna impedance with thin wire dipole due to P.S. Carter back in the 30s. And then differentiation and Newton's method, or just calculus, came up with a better approximation, really accurate approximation that almost agrees with Shelkonoff's blue curve. So the most accurate curve is the black dashed curve. And that's the one I came up with. And I also came up with another one you can't see, but it's a yellow dashed curve that almost tracks the black curve. That was also quite accurate. And then the I-Elliott cubic polyfit is the red curve. That's pretty accurate. That's the one that's in the Antenna Engineering Handbook up through the 3rd edition. I think they dropped it in the 4th edition. So we've got that problem solved, and there's an equation in the antenna book, 24th edition of the antenna book, that gives you the K-factor curve, the mathematics for it, and explains it, and it's is the most accurate K-factor curve. So if you have a dipole that is a thin wire dipole with a given wire diameter, you can calculate exactly what the resonant length will be as a function of length in free space. So now you bring in the ground. That's another complication. But this curve is for an antenna that has nothing around it. So this is for a dipole in free space. Okay, next slide. But a moments is inaccurate because the delta gap model source models are a problem. That's the reason why the ARRL's second curve wasn't accurate, but they've dropped that curve now and they're publishing my curve. So that's good. Next slide. NQ. Go to the next slide. Heinrich Hertz. He had the fields of a dipole all worked out. These drawings were done in 1888. Didn't have a computer. Don't know how he got such beautiful figures, but let's go to the next slide. We'll see what a computer can do. Whoa, it looks the same. Isn't that amazing? In 1888, Heinrich Hertz, this is before radio. This is like the beginning. This is like the verification of Maxwell's equations. Heinrich Hertz had figured out what the fields in space of a dipole had to be. Here we see a modern, and this is actually an animation, but the PDF file is not animated, so you can't see it. I've drawn a circle around the region inside of which we have what's called the reactive near field or the inductive near field, and outside of which we have radiation fields. And yeah, so inside the circle we have the inductive near fields, reactive near fields. Outside it we have this transition zone where we're transitioning into pure radiation. So the wave gradually converts to a TEM, transverse electromagnetic wave, going away from the antenna. But that doesn't happen instantly, and it doesn't even happen at this boundary. It happens gradually as you move away. But by the time you're a few wavelengths away from the antenna, the wave has been formed, and you have a transverse electromagnetic wave that travels away from the antenna all the way out to infinity in principle. So what's the radius of that sphere? 3 radian lengths. That means it's about, well, 3 radian lengths. Pi is about 3. So it's about 180 electrical degrees, or it's about a half wavelength. Actually, let's see, the antenna in the picture is a half wavelength. So it's 2 wavelengths, 2 half wavelengths. It's a full wavelength. The radius is 1 wavelength. The diameter is 2 wavelengths. Now, if you measure the electric field and the magnetic field inside this circle, and the circle is a figure of revolution, so it's really like a sphere. They're not in phase. But as you get far out from that circle, they are in phase. Electric field and magnetic field are in phase. So that's why the so-called impedance of free space is a real number. It's not a complex number. It's not an imaginary number. It's a real number because the electric field and the magnetic field travel together. They coexist, they travel together, and they're in phase. Whereas inside, they're in quadrature phase. There's a 90-degree phase shift between the electric field and the magnetic field inside of that circle. That's kind of interesting. Okay, let's move on to the next slide. Definition of Q, the fundamental definition. Q of a system is the energy stored in the system divided by the energy dissipated per cycle times 2 pi. Energy dissipated per cycle has another name. It's called power. So it's the rate at which energy is being dissipated. So it's power. So mathematically, we write energy stored divided by power dissipated is Q. Okay, but this is true for any system. So it's also true for electromagnetic systems. So it's also true for antennas. So where is this energy stored? Well, it's stored in the picture I just showed you in space in the form of fields. The electric field stores energy and the magnetic field stores energy. The total of all that energy that's stored in those fields gets divided by the power that's going out to infinity and reaches the far field. Okay, that's the Q of the antenna. So let's go to the next slide. Well, the only question in using this definition is, and this is still a matter of debate because we're discovering new things. What is the stored energy and what is the not stored energy? Knotted waves, that's the whole point. When you talk about the stored energy, do you include the energy that is not reactive, but is real, represents real power, but isn't reaching the far field? In other words, what do you put in the numerator? What do you put in the denominator? With fields, you can have energy that's stored in the fields that's reactive because electric and magnetic fields are out of phase, but you can also have energy that is not reactive, but real energy, but isn't traveling out to infinity. It's traveling in a path that's closed on itself. We call this situation a situation where the pointing vector is a solenoidal field. It has zero divergence. So the pointing vector forms a closed loop on itself, and the energy just goes in a circle, like an electronic flywheel. But it's real power. It's not imaginary power. It's not reactive power. It's real power that's just going nowhere. So do you include that power in the numerator or the denominator of this calculation? So that's one problem. And the other problem is simply that when you integrate over all of space, this energy, the numerator and the denominator of our Q definition turn out to be infinite. So you have to be very careful how you do your integrations, how you add up the power, because you're going to subtract one infinity from an infinite quantity from another infinite quantity, and you have to do it the right way. All the students of calculus know Cauchy principal value, integral theorems, blah, blah, blah. So, but that's the thing you've got to watch out for. Next slide. Okay, I've already explained this. We can go to the next slide. So let's look at some Qs of some antennas. These are Qs of ideal antennas that are of different geometries based on their shapes and dimensions and frequency. So here's a formula for the Q of a dipole. You can see it depends upon the length of the dipole and the diameter of the dipole and the frequency of operation and the speed of light and the constant pi, and it has a natural logarithm in it. And this, and all that together gives you a Q of this dipole. Okay, let's look at another antenna, the next slide. A loop. Let's look at a loop, and here we've got the same situation. The Q can be written, and it depends upon the dimensions of the loop, the diameter of the wire that makes the loop, speed of light, pi, and a natural logarithm. So we have a nice closed form formula for the Q of the dipole and the loop. Let's look at another antenna. This one will be a bent L. Or you could call it a droopy dipole. Some people like to call this the droopy dipole drawn vertically. So it's a dipole where the ends bend down. You can also put it over an infinite ground plane and call it an L over a ground plane. And so we have another slightly more complicated formula, but again, it depends on all the geometrical parameters. In other words, the shape of the antenna and some constants. Speed of light, pi, natural logarithm pops up in two places. Okay. Next slide. So we have these formulas, and we can work out these formulas. If you love algebra, this is what you should do. It's a good retirement hobby. Figure out the Qs of all the shapes of antennas you can think of. Some people have tried to come up with a different approach to Q based on the evaluation of the properties of the impedance of the antenna at its feed point without looking at the fields. Yes, without looking at the fields. Question is, can you determine the Q of the antenna just by looking at the feed point impedance and how it varies with frequency? Well, so here's 4 attempts. Series RLC equivalent circuit is one all hams should know. It's X over R. X over R. X is a function of frequency, R is a function of frequency, but the ratio is Q. So now we've got a Q that's a function of frequency, and that's true for series RLC circuits, series and parallel RLC circuits. That's where that formula comes from. And for those circuits, it is the correct formula for the stored energy divided by the dissipated power. For general circuit, it's not. So people came up with a second formula. Gaillet comes up with this formula that depends on the reactance and the derivative of the reactance. Yajian and Best found that unsatisfactory. They came up with this more complicated expression that also includes a term that involves the derivative of the real part of the impedance. See where this is going. People coming up with ever more complicated formulas because each formula before it is not good. Hansen and Collin came up with this bottom formula. It's probably the best of these terrible formulas, but it's wrong too. We'll see why they're wrong in a moment. But you cannot actually measure the Q of the dipole of the antenna on any measurement you make at the feed point or any other feed point. You can slide the feed point around. It still doesn't help. You have to go to the fields and integrate the power in the fields to get the Q, to get the real Q. Otherwise, you're fooling yourself. Okay, next slide. Oh, the Chu bound. Chu bound, I'll just mention it. L.J. Chu came up with a formula that said that the Q of any antenna has to be greater than a certain lower bound. And he published this, and it became gospel for years, and then people started picking away at it. But so far, all of the picking away has just been little technical nits. It hasn't been fundamental. Basically, the antennas, getting a low Q antenna is very hard if the antenna is physically small. Now, the nit with Chu's method was he only computed he only included in his formula or based his formula on the stored energy outside of a sphere that encases the antenna. So you look at the smallest sphere that circumscribes the antenna, you compute the stored energy outside of that sphere, and that goes in the numerator of the formula. And so his Q is based on that assumption. And what Hansen and Collin did was they added this extra energy that's stored inside of that sphere, and they got a slightly different answer, but it behaves the same way. So regardless whether you use the Hansen-Collin formula or choose original formula, you get the Q of the antenna. And what it says fundamentally is that the Q is varies inversely as the cube of the size. So if you take your antenna and make it half as big, cube of 2 is 8. So the bandwidth will change by a factor of 8. It'll shrink by a factor of 8. If you reduce the size of the antenna by a factor of 2, you reduce the bandwidth of the antenna by a factor of 8. Okay, so as the antenna gets electrically small, the penalty is very fast. This is the The people who are the most interested in Q are not hams necessarily, but it's people who want to build electrically small antennas. There's a huge body of literature on electrically small antennas that is just full of ideas on how to force the Q to violate the Chew bound.
Steve,
Yes, question.
joke comment. That's not 8 factorial. Haha.
Thank you. You are correct. That's not 8 factorial. That would be a big, even bigger penalty than the one I mentioned. Question in the back. Go ahead. Yes, it's the reason why when you see these looped antennas that are sold at Pacificon, you know, the 1 meter loop made of coax, that you have to have the big resonating capacitor. Those antennas have very narrow bandwidths because they are electrically small. Whereas if you had a big loop, they wouldn't be as touchy to tune. Okay, let's go to the next slide. We've covered the Chew bound enough so you know what it is. Let's go skip. We can skip this. This is technical. Now it's possible to make antennas that have a Q, but that appear to not have a Q by these formulas. So let's see how to do that. Next slide. There's 4 ways that I can think of. Maybe you can think of some others. But these are 4 ways, and some of them are classical and some are my own invention. But one is you take 2 antennas that are complementary antennas, so their impedances are duals. Now, the word dual means something special to engineers, so I won't explain what it is, but it's like the admittance of one antenna behaves like the impedance of the other antenna and vice versa. And then when you combine them, when you combine these 2, either in series or in parallel, you get an impedance that doesn't vary with frequency. You get an impedance that is flat and broadband, but each antenna by itself has their fields in space, and both of them are finite, definitely positive Q antennas. So you haven't affected the fields in space, but you've affected the feed point behavior. The second approach is what's called a reflectionless match network, and I've described these at Pacificon a few years ago. Reflectionless filters and reflectionless match networks are networks that look like a resistor when you're looking into them. So if you look in and you see the reactance isn't there, then you say, no reactance, Q equals 0. But it's a trick. They're a trick. What people in linear systems theory would say is that I've created hidden modes so that the system that is quote unobservable, meaning that you can't tell what the antenna is doing by looking at anything going on at its feed point. Non-Foster match networks is my own invention. That's another, or the technique I'll describe as my own invention. That just requires that you make a network that looks like the inverse of the antenna's reactance. Stick it in it, and they call that the match network. I'll show that on the next slide. And then metamaterial radomes, putting metamaterials around the antennas, surrounding the antenna with a sphere made of shells of materials in the right order, can do the same thing as a network. In fact, it's generally true that you can match an antenna on either side, either the space side or the feed point side. You either put electrical network at the feed point, or equivalently, you can put something on the other side of the 2-port, thinking of the antenna as a 2-port, which is a radome that surrounds it completely. And if you design them with the right properties, it will also impedance match the antenna.
Question.
Andy, go ahead.
Yeah, are those last 3 actually used anywhere in hardware implemented?
There's a huge amount of research being done on metamaterials right now, and this was the original motivation, was to make broadband antennas using metamaterials.
Does it really work that way?
I would say that people have been chipping away at this problem for 15 years, and a lot is known, but the fundamental problem's not solved. It's somewhat like nuclear fusion.
Also, these are only theoretical. Nobody actually builds them.
Oh, people have built metamaterials for sure. In fact, the first metamaterials were called dielectric lenses made out of metal rods, done at Bell Labs. So
May I finish with another joke comment?
go ahead.
A dummy load has 0 Q, right?
What has 0 Q? Oh, yes. That will do it. That will do it. You get no radiation. So then what the question is, what is the stored energy? 0. But so then you got 0 in the numerator and the denominator. It's pretty hard to evaluate. I guess with dummy loads, you use what's called L'Hopital's rule in calculus. Okay, let's go on to the next slide. I'm going to show you a way to make a constant resistance network. So here we have a load that looks like a series RLC on the right. We have a matching network in the middle, in the dashed blue line in the middle. And we have our feed point on the left. And the impedance looking in, if I set the values correctly, then the impedance looking into this network is a pure resistance with no reactance across all frequencies. So it looks just like a resistor. This is called a constant resistance network. This has been known to network theorists for a long time, probably since about the 30s. So let's go to the next slide. We'll look at implementation. Let's go to the next slide. I'll show it on a Smith chart. Okay, so we have our dipole. So what we're going to do is we're going to take our dipole and either make it a little bit short so that it's not it's not going to be a 75 ohm. We want to make it short so that the real part of the impedance lands on 50 ohms. So where the red curve crosses the unit resistance circle on the Smith chart, that's our dipole length. In this case, it's about 0.43 wavelengths. Instead of half a wavelength, it's 0.43 wavelengths. If I was doing this with monopoles, I'd do the same thing. I'd cut the monopole a little bit longer than a quarter wavelength, because I want its impedance to land on the unit resistance circle on the Smith chart, where the blue curve crosses that circle. And so I end up with a 0.27 wavelength monopole over infinite ground plane. Now that's just to get the real part of the impedance to be 50 ohms. Now I've got the reactance of the antenna to deal with. So let's go to the next slide. So what I'll do in the case of the dipole, I'm going to add a series resistance to cancel out the reactance at the design frequency. And then I'm going to add in my parallel LC with series R. Series R is 50 ohms, and the parallel L, the L and the C of the parallel network are given by the equations on the right. When I put all that together, lo and behold, I'll get a constant resistance of 50 ohms looking in to the right. And I don't need to use a transformer in this because I made those adjustments to the antenna lengths. If I didn't make those adjustments to the antenna lengths, then I would have to put that ideal transformer, because I might end up with like R equals 80 or R equals 100. And I've got to use a transformer to bring it to a 50 ohms resistive value. Okay, let's go to the next slide. We'll all frequency. That's the whole point. We're making a broadband 50 ohm load. We're making the dummy load, but not using just a 50 ohm resistor. We're doing it a little bit more intelligently. Question in the back. No. So this is the whole point. I'm fixing the feed point to look like a pure resistor, flat at all frequencies. This has nothing to do with what's going on in the fields in space. It has nothing to do with the Q of the antenna, but it will have a lot to do with the Q of those formulas. So this is why we're going to make an antenna that has an apparent Q of 0, not an actual Q of 0. So the network performance on the dipole, I carry out the design recipe I've just showed you. And here's what I get. SWR curve is on the top left, real and and imaginary parts of the impedance. On the bottom curve on the left, the real part is 50 ohms. The reactance is 0 ohms. And that this is from 1 megahertz to 8 megahertz on that thin wire dipole, that 98.4 foot dipole. And if I put it on the Smith chart, the impedance is that little dot very close to the center of the Smith chart. Isn't that interesting? And that's for a 100-foot dipole. 1 megahertz. Actually, you could go below 1 megahertz and you could go above 8 megahertz. I just graphed it from 1 to 8, but it works out of the band just fine. Okay, so this is just using a constant resistance network theory to design the matching network for the antenna.
Question,
Go ahead, Andy.
why is the red line in the lower curve going negative?
Reactance can be positive or negative.
Oh, that's reactance, I'm sorry. Yeah, okay,
Resistance is always positive.
never mind.
Yeah, we're just moving. If you look at the little dot on the Smith chart, it's slightly below center axis. That means the antenna is just slightly capacitive. And that's what Andy's noticing on the Cartesian graph on the bottom. Okay, next slide. Power delivered. This gets to your question you asked about power. The antenna is still narrow band. So now what do I do? If I was to compute the SWR bandwidth, that looks wonderful. But if I compute the radiation bandwidth, it looks terrible. I mean, it's no worse or better. It hasn't changed. So when you do these kinds of comparisons, you have to compare, if you normally are thinking in terms of a 2-to-1 SWR bandwidth, then you have to, when you're looking at insertion loss, you have to go with a 0.5 dB insertion loss bandwidth, because those are comparable. That's right. That's right. It's a W load at all frequencies except the design frequency where it radiates. Let's back up to the topology. Go back up about 3 slides to the circuit. Okay. So you notice that this matching network has a resistor embedded in the network. Who puts resistors inside their matching networks? Is that a good idea? Bad idea, right? Here's what that resistor is doing. Current comes in from the source and it divides. Some of it goes into the antenna and some of it goes into the matching network. When you're close to the design frequency, the resonant frequency of this thing, all the current goes through the antenna and none of it goes through this other resistor that's inside the network. As you shift off of the design frequency, less energy goes into the antenna's radiation resistance of 50 ohms. And instead it gets shunted into the second resistor that I've added. So all the energy that goes in goes somewhere, but it's a continuous shift, smooth variation from one resistor to the other resistor as you vary frequency. And that's what we're seeing on the, if we now jump forward 3 slides, we'll see, there we go. There you can see it's happening. What we're seeing is the insertion loss, 0 at the design frequency, and then it walks away from 0. But the SWR doesn't walk away from 1 to 1. All that's happening is the power that would have gone into the antenna is now going into that extra resistor. So this network makes the antenna appear to be 0Q. Okay, let's go to the next slide. And the next one after this, just more examples. Let's skip this example. Skip this one, skip this one, skip this, skip this. This is just another example. Now we'll get to Darlington. We'll mention Darlington. Sidney Darlington was a famous engineer at Bell Laboratories. Anybody ever hear of this guy? Yes. That's not what he's most famous for, but yes. The Darlington transistor is just 2 transistors connected and in a certain way, and so that the 2 transistors act like a single transistor. Okay, there's another There's another variation on that connection called the Zizakli pair. The Darlington pair and the Zizakli pair are the two interesting ways to connect two transistors to act like one transistor. One uses an NPN and a PNP, and the other uses two PNPs or two NPNs. So that's the difference. In one connection, the Darlington, both transistors are of the same type, and in the Zizakli, the two transistors are of opposite types. Okay, Darlington, what is he really famous for? Well, he's really famous for a theorem, a mathematical statement in electrical network theory, probably the second most important result after Foster's reactance theorem. And it says that any impedance whatsoever can be represented as a lossless two-port terminated with a constant value ideal resistor, one resistor. It doesn't matter what the impedance comes from. It doesn't matter whether it's a circuit or even an antenna. You can represent that impedance by a lossless two-port being terminated by constant value ideal resistor. So it never takes more than one resistor to realize any impedance function. Okay, but what's interesting is this lossless two-port, because he actually shows how to construct it. Darlington synthesis is all about how do you construct the reactance two-port so that it gives you the desired impedance behavior. So it occurred to me, well, if I can construct two ports, then formally I can invert those two ports and come up with a mathematical inverse so that when you connect two networks in cascade, they cancel each other out perfectly at all frequencies. The only problem is, before I say the problem, if one network is lossless, the other network will be lossless too. Both networks will be lossless, but you connect them in cascade, they cancel each other out. And then the impedance looking in is just the same as the termination resistor that's at the far end of that second two-port. Said, well, that's a recipe for constructing a theoretically ideal matching network. Matching network you can put on any impedance curve whatsoever, and it will transform it into a pure resistor just by determining the Darlington reactance two-port and then doing formal inversion on it. Let's look at that. Let's go to the next slide. This just states what I've already said, so we can skip it and go to the next one. So here's some pictures. We have a Darlington antenna model on the right. Here's four ways to do it. I call them canonical forms, 1, 2, 3, 4, four canonical forms. And they all have the antenna and antenna impedance model as a reactance two-port terminated by a resistor. And then in front of that, I've got four different ways of implementing an ideal inverse network, which gives you infinite bandwidth matching network. Now, this takes us into a theory of what's called non-Foster networks, which I'm not going to go into. But this is just to show you that in principle, this can be done. There's a huge literature on this. If you read the circuit theory literature and the microwave literature, this is a big topic, has been a big topic since around 2007 or thereabouts. Okay, let's go to the next slide. I've seen these four formulas. I've also shown you that we can modify our antennas by putting structures into the antenna, either at the feed point in the form of lumped elements or transmission lines or electromagnetic structures that implement those lumped elements, because after all, a capacitor is an electromagnetic device, and so is an inductor. We can put those structures, build them into the antenna as part of the structure, call it part of the antenna, and by that manner, we can cause the reactance to go to zero, the derivative of the reactance to go to zero, the derivative of the resistance to go to zero, and every one of these formulas will give you zero. So the Q of the antenna, I've given you four ways to make a zero Q antenna, four different strategies, so that you can make an antenna that at its feed point looks like it has 0 Q, yet it really won't have 0 Q, but it will look like it has 0 Q. So it doesn't. That's the whole point. The radiation is whatever the antenna had before. These are just tricks that show you that the Q formulas cannot be right, that these Q formulas cannot be right. No Q formula based on feed point impedance can be right. The only way to calculate the Q of the antenna is by integrating the fields and getting this actual energy stored. Right, that's right. That's feed point Q. Okay, next slide. This just repeats what I said. We can skip it. Let's go to the next slide. Every ham wants a big antenna. Well, I thought, here's a few I'd like to have in my backyard. The one on the left, WLW, the nation's station. Does anybody know the history of this? I know one guy in the back who's raising his hand does. Probably eager to tell us, but WLW was one of the early AM broadcast stations before there was an FCC and before even there was an FRC. So it precedes the FCC and the FRC both. And in those days, a guy named Crosley wanted to get into AM broadcasting because he made receivers. And he said, since he was in the receiver manufacturing business, he said, I should be in the transmitter manufacturing business too, because I want to have program material so I can sell more receivers. So Crosley built WLW, first high-powered AM station. Boy, was it high-powered, 500,000 watts. And to make sure his power got out, he didn't want to waste it. He made his antenna 831 feet tall. We have a really powerful station on a really tall antenna, and it radiates really well. This led to a bit of history that's kind of interesting. I don't know the full history, but it led to the war between NBC and CBS. Because when the FCC or the FRC was adopted, came into existence, NBC wanted to build a small number of stations that would serve the entire United States. Let's just cover the whole United States with like 1 or 2 stations. WLW had shown this can work. You could hear this station everywhere in the continental United States. Everywhere means you could hear it in California, you could hear it in New York, you could hear it in Florida. It's in Ohio. Yeah, near Cincinnati. CBS wanted the opposite. They said, no, broadcasting should be local. We want to serve local community markets. We want thousands of stations that have small footprints. So the FCC or the FRC had to, weigh NBC's arguments for a few big mega stations versus CBS's arguments for a large number of small stations. When they set the 50,000 watt clear channel requirement, WLW was throttled back to 50,000 watts, to 1/10 of its power. So it worked as a clear channel station for a number of years, but that all changed when World War II came along. What do you suppose happened? Voice of America did not exist. We wanted to transmit broadcasts, some would say propaganda, but broadcasts into Europe. They turned the station on, full power. It got into Europe just fine. Before Voice of America existed, we were delivering our broadcast to Europe by AM radio. Yeah, 680 kilohertz. Right now it's 700. They shifted to 700, but it was 680, I believe. Yeah, it's AM broadcast. Okay, they had plans to go to a megawatt. In fact, they had already done all the engineering calculations. They submitted the service contours, everything to the FCC. I don't think it ever got approved. I don't think they ever went to a megawatt. The station still exists. It's a museum. You can take tours of the big transmitter. If you want to see a really big transmitter, Go there. Building is still there. Yes. Yes. Let me say that antennas can be really big because they're really broadband, like the Green Valley HF disc cone. This is a full band HF disc cone at Green Valley, Arizona. It's at the Titan Missile Museum. You can operate it. You drive into the parking lot, there's a little box. You know, everybody remember what drive-in theaters were like. You drive up, you roll down your window, you pull in the little loudspeaker, hang it on your windowsill. Same thing here. You drive up, park your car in a stall, roll down your window, reach in, open a little door, pull out a coax, plug it into your rig. So your car can plug into this antenna and you can operate it. You can operate this. I was down there with my little QRP radio and man, this was wonderful. So that's only 80 feet. But it's really broadband and it's really cool. One on the right will be more familiar to all of us. Anybody that is in the Bay Area should recognize that. Sutro Tower. Not just one antenna, it's many antennas on this tower, but this tower has so much RF on it that when you work on this tower, you have to put on a radiation suit. And then you take the little elevator up the leg. There's a little platforms at various levels you can get out and do your work, but you have to wear your radiation suit because they cannot turn all the transmitters. They will not turn off all the transmitters for you, just so you can work on one transmitter. 977 feet. Antennas are interesting not only for their electrical behaviors, but for their mechanical design issues. So it's interesting, mechanical engineers sometimes think it's better make the middle of the antenna skinny and the top and bottom fat, like Arnold, or the opposite, make the middle of the antenna fat and the top and the bottom skinny, like Santa Claus. And as far as I know, both techniques work. This one requires guy wires. That one does not require guy wires. So maybe that's the difference. So there are interesting challenges if you're a mechanical engineer, figuring out all the stresses and the strains and doing your statics calculations and your wind loadings and all of that, which is just as fun. Dave. There you go. That's right. They had a long wire antenna on the top, along the top. Yeah. No, I think, well, usually not. Usually antennas are little bunker or blockhouses or little vans built in at the base. But I don't know for every station how it's handled. But if you're going to put them on the tower, you've got to bring AC power up to them. Yeah. Dave, do you know the answer to that? I don't know the answer. Oh, that's WLW. How about Sutro? I think all the antenna, I think the transmitters probably are all on the ground. And they just feed coax up to the antennas. That's what I think. Yeah. We lost coax. Okay, let's go to the next slide. We're having too much fun. Okay. Even bigger. I showed you big antennas, but now I'm going to show you even bigger antennas, or at least one. This is the Duga, the woodpecker. It's called the woodpecker. Built by the Soviet Union because they wanted to detect, use over-horizon radar to look over the North Pole to watch the missiles from North America coming toward them. They were paranoid about the US shooting missiles over the North Pole, so they built this radar. It's massive. 2,300 feet long, 490 feet high. It's an array, it's a phased array of dipoles. I don't know, there's more than 100 antennas, dipoles in that array. I think it's like 20 by 30 or something. It's a big number. Duga, called the Duga or the Duga radar or the Duga system or the woodpecker. The hams all call it the woodpecker because of the noise it made on HF. It's still there. There is a conspiracy theory that you will find on the web that the reason for the Chernobyl power disaster was an attempt to prevent the discovery of the existence of this radar. This was far more valuable to the Soviets than the Chernobyl power plant was. And they think that that the orders came from up high in the government to blow up Chernobyl so that it would keep people away from this. And this is actually in an area where you don't visit anywhere. It's in the now it's in the nuclear exclusion zone. You can still get there if you want. Oh, it was massive, massive. Okay, let's go to the next slide. We've seen some big antennas. We've looked at, here's some misinformation. Now, misinformation is something there's a lot of, especially in the amateur antenna literature, but even sometimes in professional antenna literature. But usually in the professional literature, it's just typos, typographical errors or simple mistakes. But sometimes there's stuff that's just flat wrong or wrong-headed. Many of you may remember that QEX magazine had a long-running debate back in the 1990s about conjugate power matches. And anybody remember that? Well, it was Walt Maxwell's doings. Walt Maxwell versus the rest of the world, basically. It actually started in QST magazine in the mid-1970s as a series that ran from about 1973 up to about 1976. And then that was all combined. Those articles were combined into a book called Reflections. And then there was a long-running debate that went from Communications Quarterly magazine, Communications Quarterly into QEX, then into CQ, then into World Radio newsletter, with Maxwell debating everybody in the world about conjugate match ideas. Ultimately, Maxwell is wrong on so many points that it was laughable, but people still admire his book as a work of BS. Okay, everything he talked about was for lossless transmission lines, not real transmission lines. And if you read his appendices in his book carefully, you'll realize that in his conception, transmission lines are not symmetrical devices. If it exhibits loss going from one end to the other and you turn it around backwards, now it will exhibit gain. So that's interesting because all the transmission lines I've seen are symmetrical devices. You turn them around backwards, they work exactly the same. Anyway, I digress. Here we have a graph. I'm going to point out three things wrong. First is the title, dipole radiation versus dipole size and wavelength. I have no quibble with the dipole size and wavelength. I have quibble with dipole radiation because it doesn't really quite tell me what he's talking about by radiation. Because when he presents this graph, I don't know if this is a graph of gain or directivity or what aspect of radiation it is. It's just called relative radiation in decibels. But he sets the zero, so it corresponds to a half wavelength dipole. So here's a half wavelength dipole. And you go up to the curve, and that's where the zero is. So is this dB? Is this dBd? dB is relative to a dipole. That's the logical conclusion. This is dB's relative to a dipole, but radiation in dBd, we know for a fact that the gain of an infinitesimal dipole doesn't go to zero or minus infinity dBd. It only drops down by a fraction of a dB, from 2.15 down to about 1.76 dB. That's the difference between an infinitesimal dipole and a half wavelength dipole. It's about 0.4 of a dB. Because the patterns don't change that much. And if you're dealing with lossless antennas, admittedly with an infinitesimal dipole, there's an impedance matching issue, but that's different from an efficiency issue due to losses, because if both antennas are lossless, then the only things I have to compare are their directivities, and the directivity difference is only 0.4 of a dB. But he's got minus 65, almost minus 70. Well, that's the complaint, is that the word relative radiation doesn't tell me what the heck he's talking about. Relative to what? And relative to what aspect of a dipole? The other complaint is, well, and so that implies that the units are misleading, because you're led by this picture to think somehow it's dBd, because it is dBs relative to a dipole, but we don't know what we're talking about. So that part's confusing or misleading. The other thing is, when you actually look at this, what this is a graph of is the real part of the radiation resistance expressed in dBs, except if you did the conversion wrong, you got an extra factor of 2 in there. This is simply radiation resistance, the real part of the impedance, divided by the dipole impedance of a half-wave dipole, real part of that impedance. And this graph should only go down to 35. So he's got an extra factor of 2 cranked in. So that's another mistake. So everything on this graph is wrong. The only thing that's right is the abscissa and the label on the abscissa. Everything else is wrong. Okay, let's go to the next slide. That, by the way, that's from a ham publication. I'm not going to identify the culprit. If you run across it, you'll know. Noise figures of antennas. Well, this is how you can compare antennas, is by comparing their noise figures. And so we see that different types of antennas have very different characteristics in their noise figure. And so we can rank our antennas in general categories just based on noise figure alone. And so what we find is, at low frequencies, the best antenna with the lowest noise figure is the vertical dipole. Second best is the vertical loop. The third best is a horizontal dipole. And the fourth best is the horizontal loop. As we go up in frequency, these curves cross. So at the upper HF band, the order is different. At high frequencies, like 10 meters, we'd have that the horizontal dipole is the best. The vertical dipole is second best. The vertical loop is third best, and the horizontal loop is the worst. So the only thing you can say is the horizontal loop is always the worst. This graph doesn't, it's based on how antennas process noise, how they process external noise that's received on the antenna, and ground effects. This was, I think, ground effects. This was done over. These curves are specifically for antennas located a certain distance above an average ground. And the external noise is galactic noise. So I think atmospheric noise might have been left off of this graph. So this graph is for galactic. So the other noise sources that come into play that are not included but could be included would be close-in noise sources. This is just assuming distant galactic noise. Yeah. Yeah. Right. Exactly. So here's where it was published. Steve Best, Radio Science, December 2016. So it's relatively recent research result. Okay, next slide. Okay, what are the best software packages? Well, it used to be everybody used 4NEC2 as the GUI, which ran the NEC2 engine. But NEC2 has a lot of limitations. And it can give you wrong answers, and you won't know it.
Comment.
Go ahead, Andy.
I like 4NEC2.
Good. Good for you. Please use it. 4NEC2 is a wonderful GUI. I like it better than EasyNEC because it gives me more command and control. EasyNEC only brought out a subset of all the NEC commands to the user, whereas 4NEC2 gives you access to the entire command suite of NEC2. However, the NEC2 program itself is the source of the inaccuracy, apart from the GUI. So that's the two issues: is how good is the GUI, the graphical user interface, how easy is it to use, how is it easy to set up models, how how much flexibility does it give you? And then there's the question of how accurate is the calculation engine? And the next two calculation engine has a lot of tricks that you, or I should call them rules of thumb you have to adhere to, or you get bad answers. Same thing is true of NEC 4. We used to think NEC 4 was the gold standard, but now not so much. So the older versions of EasyNEC, or what the British use is Manigal, which is based on MiniNEC. That's another one that also has its own set of disadvantages. And then even earlier, we had AWAS, sort of analysis of wires and scatterers or something. That was out of the Popovic, Dorjevic, Kalunzia school of thought. I think Kalunzia was not in there, but Dorjevic and Popovic were. Very fine code in its era. And then Whipple D Lite was a very fine surface meshing code available to hams, but considered an antique today. So what are the codes that I would recommend today if you were to go out and buy one? ANSOF or NEC 5. If you go with NEC 5, you're going to get a license for NEC 5 from Lawrence Livermore Laboratory, $110. You're going to download the free EasyNEC GUI from the EasyNEC site to run it, because it's much easier to use that GUI than it is to use what comes native with NEC 5. And then because you're going to want to have an optimizer, and EasyNEC doesn't give it, and neither does NEC 5 have it, you're going to download the Auto Easy from Dan McGuire, AC6LA, that costs $80. So for less than $200, you can have a really fine wire antenna modeling suite that's accurate, easy to use, will let you play with antennas, geometries, ground models, and so forth. The alternative is ANSOF, which is in the price range, only a little more expensive, $350 to $450, depending on service contract terms, I guess. How many years, how many upgrades they give you or something of that nature. But ANSOF is very accurate. In fact, we can't tell which of these is more accurate. Both of these codes almost always give exactly the same answers. It's quite amazing. They're both more accurate than NEC 5 or 4 was. And so if you're going to spend money, oh, and there's another thing I'll just tell you, I'll give ANSOF a plug. They're coming out with a new release. I think it's version 8.5 is coming out next week. Right now they're running a, what do you call it? A sale, 30% off. So you get a $450 code for like $300 or something. If you go to their website and download it. I don't know when it expires, but it's only a few, through the weekend maybe. So ANSOF is running that special, but even without the special, the price of this is affordable. It's within the range where the hams who do a lot of antenna modeling will appreciate it. Code I used to recommend, I still recommend it, but it's not available, so I can't really push it very hard. It's Hobbies, high order basis function. That's a surface meshing code that came out of the Popovic, Dorjevic, Kalunzia school of thought. It competes directly with the Whipple D professional software. And in my opinion, Hobbies is the better software. Hobbies is better than Whipple D because the software architecture is better. The user interface is much better. So Whipple D does exactly the same, but the professional version is, $50,000. The Hobbies was like 200, but it's not available. So those are the codes. So let's go. I think that's it. Oh, books. I always like to show a few books. The new 25th edition of the antenna book is coming out this year, later this year. So don't rush out and buy the 24th edition unless someone's selling it like 50% off or something. Then you might get it. But yeah, so the new antenna book is coming. The standard textbook nowadays is no longer J.D. Krause. It's Constantine Balanis. He's at Arizona State University. His antenna book is in 4th edition, and it's a very fine book if you are interested in learning about antennas. That's the textbook that you should use. The German ham book, Ralph Hammel's Antennenbuch. And it is now translated into English, and you can buy it from Dark in Germany, and they'll ship it. The shipping will cost as much as the book. But you're getting your money's worth because that book is heavy. That book is as heavy as the Antenna Engineering Handbook. It's a big, fat, dense book with lots of bibliographies and references. So if you do research, that's a good book. I have both editions. I bought the German edition right like 2 years before they came out with the English edition. So then I bought it again. And then little books. If you want a book on small antennas, then I can recommend a small book. R.C. Hansen and R.E. Collin, Bob Hansen, Bob Collin on small antennas. This is essentially the second edition of Hansen's first edition. His first edition was the green book. This is the gold book. And that talks about a lot of myths and flaky antenna concepts that don't work in the real world. And that is it. We can go to the final slide is just that.
Okay. So
Questions, anybody?
actually, Steve, what we'll do here is we'll take questions in the room, and then anybody on Zoom, put it in the chat, and then I'll turn it over to Ben to moderate the chat questions so we don't get doubles.
Unnecessarily large. They would have been better to have had them half the size with the proper matching and so on.
The WLW antenna was so tall that it was creating interference with another station in Canada called CHU. And they tried various fixes, and finally they had to chop off the top 30 or 40 feet of that tower. The Blaunach's tower is not as tall as today as it was when it was built. So it was too tall. And it had to do with, basically it had to do with ground wave propagation versus ionospheric propagation and causing strong interference. That's true with generally with clear channel AM stations, is that sometimes they radiate so strongly into the near field region that they will cause funny tingling sensations in your teeth, fillings and such. So basically, yeah, antennas need to be designed for their purpose.
All right, we got a question over here from Shriek.
Yeah, so you had pictures of the Duga and as big antennas, but even bigger antennas if you count the parabolic dishes like Arecibo, which went down, and this is a Chinese 500-meter dish. Now the question is, does a dish behave any differently from the mathematics than a phased array, or is it exactly 1:1 equivalent?
Okay, the question is reflector arrays versus phased arrays. And the answer is that, you just got another layer of math to include when you do big reflector antennas. One of the advantages of reflector antennas is they don't have to be sections of a sphere or a parabola. You can put dimples in them and wrinkles. And that allows you to shape the footprint. And this is done on satellite antennas like Intelsat, Inmarsat, I don't know, the satellite services that put a footprint down. And basically, it's like a big cell, but they can tailor the cell shape so that covers the geographic territory they want. So I've seen footprints of antennas that perfectly match the contour of continental United States with a little spot out here for Hawaii. They put that little spot there because they wanted to cover the continental United States plus Hawaii. So yes, you can do fancy things with reflectors in terms of maximizing gain. You get high gain from reflectors. You can also get high gain from parasitic arrays. Big Yagis, giant Yagis can have very high gain. Yagi is a traveling wave antenna where the wave travels down a boom. It's a slow wave structure. So it sort of collimates the beam the farther it goes, the more it collimates it, and you end up squirting out the end. And it's all done by phasing the current along the way by tweaking the lengths of the elements. Other question.
Yeah, any other questions in the house? Oh, over here. As my roving camera reboots. Oh, there we go.
So this is David KM6RI. You had a slide on antenna noise figure, and I'm familiar with receiver noise figure, but not antenna noise figure. Could you say a little bit in practical terms what that is? Is there any analogy to receiver noise figure, and for hams for practical purposes? So what is the implication?
Okay, noise figure has a general definition that applies to multi-port networks. Those multi-port networks can be realized as receivers, filters, or even antennas. And in fact, the entire transmission path from the transmit antenna through the propagation medium to the receive antenna to the receiver can be modeled as a two-port, consisting of a bunch of other two ports in cascade, those being networks, transmission lines, antennas, propagation channel, and so forth. So you can think of a two-port followed by a two-port, followed by a two-port, followed by a two-port, all in cascade, and you can compute all the properties. So noise figure for an antenna is just the noise figure based on the noise at the terminals of the antenna. So it is usually done in radio astronomy terms in degrees Kelvin. But microwave engineers prefer to use decibels and noise figure in dB. Beyond that, I'll just refer you to books on radio astronomy antennas.
The question was, does the true boundary assume that the antenna is linear and time invariant, and is anything that does not satisfy the true boundary not linear and not time invariant?
Okay, the true limit is first of all, is the concept of time invariance is somewhat embedded. It's a frequency domain concept. So we're solving Maxwell's equations as a function of omega rather than t. And it's a sinusoidal steady state assumption. The true boundary is done by expansion of the fields in spherical harmonics. Fields are expanded outside of the sphere in spherical harmonics. And there's an assumption that no more than one mode is excited, or at most two modes are excited. And based on those assumptions, he gets the bound. So it's a very general bound, but it does not apply to transients. It only applies to, we'll call it narrow band signals, where the bandwidth is all compared with the duration of the signals, where the signal durations are long compared to the reciprocal of the bandwidth. And it's a narrow band assumption. So time invariance, well, yes, the systems would be time invariant under those assumptions. You could have a system that was slowly time varying as long as at any moment it acted like a snapshot of a time invariant system, and then the true bound would still apply. These are questions that are best asked as general system theory questions. Is there another aspect to that question?
No, that was it.
Okay. Okay, I hope that was a good enough answer. Any other questions from the room?
Okay, anybody else? Or otherwise, we'll move on here. I think that's it.
Thank you, Steve.
Okay. So Steve, thank you very much.